Good morning everyone. This is the last video of the capacitors and dielectric chapter. In the last video we had discussed about the energy stored in a capacitor and energy stored in the parallel and series combination of capacitors. We had also talked about polar and non-polar molecules. There was one topic that was left before discussing dielectrics was force between the plates of a charged parallel plate capacitor. Force between the plates of a charged parallel plate capacitor. So we have a parallel plate capacitors. One of the plate has got positive Q charge, the other plate has got minus Q charge, and these two plates are separated by a distance small d. Let us consider that initially the plates were very close to each other. Okay, both the positive and negative plates were very close to each other but not touching each other. So the plates have got positive and negative charge. There is a force of attraction acting between the positive and the negative plate. Now the plate has to be taken away from each other. So if we gradually pull the plates away, then to a small distance d in the uniform electric field, what will happen? There is an electric field that is developed between the two plates, plus and minus. The electric field is equal to sigma upon epsilon naught, where sigma is the surface charge density. Okay, there will be a force developed. Okay, so when a uniform electric field is being developed between the two plates of the capacitor, the two plates are moved away from each other, then the electric field is equal to sigma upon epsilon naught between the plate is maintained and the force remains constant at F. Now the work done in separating the plate from approximately 0 distance to d distance is given by W equal to F into d. So work done is stored in the capacitor as electrostatic potential energy. Whatever work that has been done in moving the plates apart by a distance d is stored in the form of electrostatic potential energy between the plates of the capacitor. So W equal to Fd, we know the energy between the plates of the capacitor or energy stored in the capacitor is given by the formula U equal to 1 by 2 QV. So we substitute the value of V. V is equal to Ed. E is the electric field and D is the distance between the plates. And instead of U, we will write Fd. So D and D cancel on both left hand side and right hand side. The force between the plates of the capacitor is equal to 1 by 2 QE. The force acting between the plates of the capacitor is 1 by 2 QE. This force is constant force. We can also substitute the value of electric field. Electric field acting between the plates of the capacitor is given by the formula sigma upon epsilon naught. So if we write sigma upon epsilon naught, and what is sigma? Sigma is surface charge density. This is Q divided by area of the plate. Total charge upon total area of the plate. So finally we get the formula for the force acting between the two plates, that is given by 1 by 2 Q square upon epsilon naught A. So this is the force acting between the plates of the charged parallel plate capacitor, where the charge on the plates of the capacitor is plus Q and minus Q. So F is equal to 1 by 2 QE. Dielectrics. A dielectric is an insulating material in which all the electrons are tightly bound to the nuclei of the atoms. There are no free electrons to carry current. Hence, the conductivity of a dielectric is very low. Or rather we can say it is a resistance of poor conductor. Example: glass, plastic, mica, oil. These are all dielectrics. Then we have dielectric constant. It is found experimentally that when a dielectric material is placed between the plates of capacitor, the capacitance of the capacitor increases to K times, a dimensionless factor. So, the capacitance of a capacitor increases to K times. That K is known as dielectric constant. So, K is equal to C upon C naught. C naught is the capacitance when the space between the plate is having vacuum, and C is the capacitance when the space between the plates of the capacitor is filled with the material. So K is equal to C upon C naught. K is known as dielectric constant or specific inductive capacity of a material. It is the ratio of the capacitance of a given capacitor completely filled with that material to the capacitance of the same capacitor in vacuum. Dielectric constant for different material are different. For vacuum it is K is equal to 1. For air K equal to 1.0006. For glass K equal to 6. For water K equal to 80, and so on. Then we will discuss the polarization of dielectrics. When a non-polar dielectric slab is subjected to an electric field, dipoles are induced due to the separation of effective positive and negative charge. We are putting a dielectric material between the plates of the capacitor. Where there is a positive plate, dielectric surface will induce a negative charge near the positive plate of the capacitor. Similarly, near the negative plate of the capacitor, a positive charge will be induced on the surface of the dielectric. Let the electric field between the plates of the capacitor be E naught. This is the applied electric field. And a positive and negative charges are developed on the surfaces of the dielectric facing the positive and negative plate of the capacitor. An electric field is also developed inside the dielectric, which is in the opposite direction of the electric field due to the plates of the capacitor or applied electric field. So the two electric fields are in the opposite direction. E naught is the electric field due to applied electric field, that is the electric field between the plates of the capacitor, and EP is the induced field in the dielectric. So the net electric field is given by En is equal to E naught minus EP. What is the result? The result is the resultant electric field is reduced when dielectric slab is introduced. So what is the action of dielectric when placed between the plates of the capacitor? When a dielectric is placed between the plates of the capacitor, the electric field is reduced. Is it clear? So the electric field of the dielectric is reduced when a dielectric slab is, the electric field of the capacitor is reduced when the dielectric slab is introduced between the plates of the capacitor. So if a dielectric substance, dielectric material of dielectric constant K is introduced between the plates of the capacitor, then its electric field will become E naught upon K. Okay. Now we will study the effects of introducing dielectric between the plates of a charged capacitor. Let C naught, V naught, Q naught, E naught and U naught be the capacitance, potential difference, charge, electric field and potential energy between the plates of charged capacitors. Now we introduce a dielectric slab between the plates of the capacitor. Then its capacitance will become C, potential will become V, charge Q, electric field E and potential energy equal to U. Now there can be two conditions. When you are connecting a capacitor to a battery, if battery is connected, key is closed and the charge is flowing to the capacitor, in that case the capacitance does not depend whether the key is closed or open. So once we are introducing a dielectric slab, the capacitance will increase to K times. So C will be equal to K C naught. Okay. Capacitance does not depend whether the key is closed or open. In that situation, the capacitance becomes K times the initial capacitance C naught. The potential difference. When battery is connected, the potential difference between the plates of the capacitor remains the same. So V equal to V naught. V equal to V naught. There is no change in the potential, whether you introduce the dielectric or whatever was the potential before, when there was air or vacuum in the between the plate of the dielectric. So there is no change in the potential before and after the introduction of the electric slab. Third is charge. We know that Q is equal to CV and C is equal to K C naught. So K C naught V naught. So Q is equal to K Q naught. That is, charge increases to K times. The charge increases to K times. This is all when the battery is still connected to the capacitor. So charge will increase to K times. Next we have electric field. The electric field is given by the formula V upon D. Now, as I have told you, electric potential does not change when the battery is connected to the capacitor. So V upon D is equal to V naught upon D. That means that V naught upon D is equal to E naught. So electric field E and E naught. E naught was when there was air between the plate of the capacitor, and E is the electric field when the dielectric is introduced to the capacitor is same. So E equal to E naught. The electric field remains unchanged. Then the potential energy stored between the plate of capacitor U is given by the formula U equal to half CV square. So instead of C, where dielectric is introduced, C is equal to C naught K, we substitute the value K C naught, and V naught are equal, so K C naught V naught square. This is equal to K times 1 by 2 C naught V naught square. Therefore, U is equal to K U naught. So potential energy becomes K times of the initial potential energy. So all these conditions over there. So when the battery is connected, capacitance becomes K times, charge on the plate becomes K times, potential difference remains the same, potential energy becomes K times. The force between the plate also becomes K times, charge density also becomes K times, electric field intensity E remains the same. Next we have when key is open, battery disconnected. When battery is disconnected, then C naught is equal to A epsilon naught upon D, and C is equal to K A epsilon naught D. When the dielectric has been introduced between the plate of the capacitance becomes K times. Now potential becomes 1 upon K times. By the formula V is equal to Q upon C. So Q naught upon K C naught. So the potential becomes 1 upon K times. Charge Q equal to CV. So Q equal to CV. C की जगह क्या रखा? K C naught. और V की जगह रखा? V naught upon K. So it becomes C naught V naught, that is equal to Q naught. Charge becomes equal to Q naught. Electric field also becomes 1 upon K times. When the battery is not connected to the capacitor, then a dielectric is introduced between the plates of the capacitor, then the electric field decreases by K times. Okay. Then potential energy also decreases by K times. Okay. U is equal to U naught upon K. Energy will decrease. So this is all given in a tabular form. You can go through it. So this brings to the end of the lesson.